Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is dominant pairs, and it is a easy level problem. So this particular problem is fairly simple, and I'll just read out the statement for you. So this particular problem says that we have been given an array size n where n is even, and we have to find the number of dominant pairs, right? So these particular dominant pairs are denoted by this particular equation, which says that I should be in the first half, j should be in the second half, and array of I should be greater than equals to 5 times array of j, right? So this relation should be fulfilled. And like if we reduce this particular thing into a mathematical statement, and it says that we have to account for every index in the second half the number of indexes that are present in the first half, such that their value is at least 5 times the value of the indexes in the second half, right? So array of I should be present in the first half, and their value should be at least 5 times of array of j, and j is present in the second half. So this is the whole problem, and let us discuss some sample test cases before moving on to the problem solution. So this is test case that we have. So it says that we have these integers 10, 2, 2 and 1, right? So these are the integers in the first half, and these are the integers in the second half. So for every index in the second half, that is this particular value and this particular value, we have to count the number of indexes in the first half such that their value is greater than equals to at least 5 times of this particular value. So first of all, we'll have to calculate the 5 times of 2. So it is 5 into 2, that is 10. Right. So how many values are present in the first half that are greater than or equal to 10? So that is 1. Right. Similarly, for this particular value, we have to calculate its 5 times. So 5 into 1 is 5. And we have to check how many values are present in the first half such that their value is greater than or equal to 5. Again, the answer is 1. So the total answer is 2. Right. So this is exactly what we have to do. Now, this particular problem can be easily solved with something like suffix sums. So for example, if we have a frequency array, so if we maintain the frequency of 0, frequency of 1, frequency of 2, frequency of 3, frequency of 4, right, like this. So if we have the frequency of all of them, and we just calculate the suffix sum of this particular array, then at position 2, I'll have the frequency of all the elements greater than or equal to 2. At position 3, I'll have the frequency of all the elements greater than or equal to 3. Similarly, for each index I, I'll have the frequency of elements greater than or equals to I. Right. So we can like implement this approach. Now the constraints also allow us to do so. So the constraints are from minus 10 to the power 4 up to 10 to the power 4. So this is the constraint on the value of a of I. Right. This is the constraint. Now we can easily apply this particular array implementation on this question. So for example, minus 10 to the power 4 will be at the index 0. So how do we do this? For every real I value I, right? For every value of a of I, let us denote it as a of I. It can be stored at position plus 10 to the power 4. Right. So minus 10 to the power 4 will be at 0. Right. The value of a of I, when a of I is equal to 0, when a of I is equal to 0, it will be stored at 10 to the power 4. When a of I is equal to 10 to the power 4, it will be stored at 2 into 10 to the power 4. Right. So we can easily create an array of this particular size, and we can store all the values, and this is the offset that we are going to use. Right. This will always work. But the thing is, like in my experience while solving Geeks for Geeks problems, the constraints that they generally give are not very actual to the actual sample test cases. There will be some values which might differ from the constraints, and in that case, like our implementation will fail. So it's like I felt it was better to do the same thing with the map. And also the other constraint, the expected time complexity that they mentioned was n log n, which is for the map. So this is the time complexity, and for the space complexity they mentioned O1, right? So I believe like it would be much better if we just directly implement a map and we don't have to think about this offset logic. But if you still want to try, I just like told you that this is also possible according to the array size that according to the values of a of I that they have given. This is definitely possible, right? So what if we want to do the same thing in a map, right? So once we have a map, we know that it is in sorted order. Right. Here we have some values in the map. So map will not be actually like this in contiguous positions. It will be implemented in some other way. So for example, I'm just like representing it in a form of an array. So for example, one value is 0 is here, and the other value is 2, and we have 5, then we have 6, and then we have 10. Right, so map will always be sorted order. So one way of doing this is I use a pointer and set it to map.end. So once I set it to map.end, it will be at a position just after the last element. Right, now I can just do minus minus pointer and I can get it this particular position. Now my current value is 0, so the current value is the value that I have calculated after all these elements, the sum of all the values after this particular element. So at every point I can just do current the value of I. So for example, MP of I, this is my current value, right? I can just add the sum from the all the elements from the right of it, right? And I can just update my sum as MP of I, because MP of I will now contain the sum of all the values starting from this particular position till the end, right? Again I can do minus minus pointer and get to this particular position. I'll update MP of I by sum, and I'll update the value of sum as MP of I, right? So this is exactly what we are going to do. We are just going to decrement the pointer until we get to the first position, right? So once we get here, we will have to break out of the statement, because like the pointer will be equal to MP dot begin, right? So once it is equals to empty dot begin, we have to break out of the statement and we'll have to implement like this for this particular index separately. So I'll explain you this with the help of the code and you'll understand much better. So as you can see here, what you have done is I've created a map, and what I'm just doing is I'm for all the elements in the first half, I'm just incrementing the frequencies. So I create a pointer and it is equal to map.n, and I just decrement the pointer. So this is the value of current, and current will store the sum of all the values to the right of the current element, right? Now what I do is, while pointer is not equals to map.begin, I just increment the value of the current point of the element at the current pointer. So that this is the frequency that is stored in the second. I just increment its value and I just update my current as pointer.second, right? Again I decrement my pointer. So once I've reached the first position, as soon as I reach the first position, this while loop will break and this particular condition will not execute. So I just have written a separate line for the first position. Now, so this is the same thing which I have written here. It's just that this is for the first element, because this will not get processed in the loop. Now, once this is done, I initialize my answer with 0, and for all the positions in the second half, that is starting from n by 2 less than n, I just try to find the 5 times of the current element array of 5 by doing binary search using lower bound. Right, so this is an inbuilt function of the map. Once I find this, what I do is, if the pointer is not equal to map.print, that means I have been able to find the value and it is present in the array. I just do answer plus is equal to pointer.second, right? So this will be added in my answer. Now, like the lower bound function will always give me the if 5 times array 5 is present in the array, it will give me that particular value. But if it is not present in the array, it will give me the just greater value. So in both of the cases, my code will work absolutely fine, because I'm just considered in the sum of frequencies of this particular value and all the values greater than it, right? So even if it is greater, then it will work for my code. Now I just check whether this is not equals to mp.end, and I add it to my answer. This will be the whole code, and at the end I can just return my answer. So this was the solution for today's problem, dominant pairs, and I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to subscribe to this channel. Share this channel with your friends. Until the next video drops, keep coding, stay safe, bye bye.